Hello everyone, this is Mr. Supnil Papu Saverwade, lecturer at Mechanical Engineering Department, Sir Institute of Technology, Polytechnic, Yadra, Vichalakaranje. Next, in this lecture we will see the chapter number 2, or we will start the chapter number 2, that is steel and its alloys. Okay. So in this we are going to see the subtopics like definition of phase, second pure metal, third alloys, and fourth polymorphism. Okay, then we are going to see the solid solutions. In that we have two types: substitutional solute solution and second interstitial solute solution. And the third point we are going to see, that is solid solubility, or we can see it as a Hume-Rothery's rules of solid solubility. Okay. The next we will start with the phase. We can define it as a phase is any physically distinct, chemically homogeneous and mechanically separable portion of a substance under study. In general, we know that phase can be a solid, it can be a liquid, or it can be a gas for pure substance. Okay. First we will go through the definition. See, what they say is the phase is any physically distinct, means physically distinct means it is a physically differentiation, means we can physically differentiate solid, liquid and gas. As we know, the physical nature of solid is different than physical nature of liquid, and it is different than physical nature of gas. Means we can physically see and we can observe that this is a solid, this is a liquid and this is a gas, so that we can physically differentiate the three phases. Okay. Next, chemically homogeneous means we can take an example of a steel or cast iron. It is a solid, then it only have the solid particles in it throughout the material. It doesn't have any liquid or gas, so it is chemically homogeneous of a steel material throughout the structure. Okay. Same way we go for the liquid. We take the example of 1 liter of water. Okay, in a jar. That 1 liter of water only contain the water in a liquid media. It doesn't contain any solid media, or it doesn't contain any gaseous media. So it is chemically homogeneous with the liquid medium. Okay, at the top, at the bottom, at the side we can get only liquid. So it is chemically homogeneous with the liquid media. Same way the mechanically separable means we can separate solid from a liquid, we can separate solid from a gas, we can separate liquid from a gas. So these all three phases are mechanically separable. You are getting or not? Means phase is something which is physically distinct, which is chemically homogeneous in their respective phases, and we can separate all three phases from each other by mechanical way. This is called a phase. In general, we have three phases: solid, liquid and gas, and phase can be pure substance or solution, provided that the structure and composition are uniform throughout. Uniform means the structure and composition will be homogeneous throughout the structure. Okay. Next we have some examples. If we mix the water and alcohol, they form a single phase, because the water and alcohol mix in all proportions, they form a homogeneous solution. So they form a single phase, that is liquid. But if we mix the water and oil, water is a liquid, oil is a liquid, but they doesn't form a homogeneous solution, they form the heterogeneous solution. At the top we have oil, at the bottom we have water due to some density gradients. Okay, they cannot form a homogeneous solution, they cannot mix with each other, so they form the two phases of the same liquid media. So here we get the two phases. Okay, you are getting or not? So after mixing water and alcohol we get single phase, after mixing water and oil we get two separate phases of the same medium. Okay, so phase is nothing but something which is physically distinct, chemically homogeneous, mechanically separable portion of a material. Okay. Next we have second definition, that is pure metal. Pure metal is something or the element which have valency 1, 2 or 3. Valency means it is a number of elements present in outermost shell, or the number of electrons which can be shared with the different elements. That is nothing but a valency. Okay. So those elements which have valency 1, 2 or 3, those are called the pure metals. Or the metal which consists of single element having same atomic size and crystal structure is called pure metal. The metal consists of single element having same atomic size and crystal structure is called pure metal. Okay, we have some examples. That is copper, valency is 1, aluminum valency is 3, magnesium valency is 2. Remember these examples, this may be asked in the online exams. Okay, so the examples are copper, aluminum and magnesium. Okay, we will go to the next one. Alloy. Alloy is nothing but it is a mixture of two or more metals or the non-metals, but the case is that in which one should be a metal. We cannot mix a two non-metals and form a alloy. Okay, so one should be a metal. It is a mixture of metal and non-metal, but in which one should be a metal. Okay, we have the example like brass is alloy of copper and zinc. In this, copper is 60%, zinc is 40%. Okay, so when we form the alloy, we have two different things or two or three different things. In that, one which have the higher composition, something which have a lower composition. So we have two things, that is solvent and solute. The element which is present in the largest amount or the largest composition is called a base metal or parent metal, or we simply say it as a solvent. Okay, and the element which is present in the smallest amount is called solute. Means which is more it is solvent, which is less it is solute. Okay, we can take an example, you can get it well. Okay, first example, solution of 1 liter of water with 100 gram of sugar. Here we mixing 1 liter of water with 100 gram of sugar, which is a higher one, 1 liter of water, so it is a solvent. Which is a smaller one, that is 100 gram of sugar, it is solute. Okay, so this is a good example to understand what is solvent and solute. Okay, look at an example in metallurgy. Okay, in steel, solvent is iron because its composition is from 90 to 94%, as it is a base metal, you know. Okay, and carbon is a solute because its percentage is from 0 to 2%, and in steel we found the interstitial solute solution. We can see the next. Okay, next one, we have another definition, that is polymorphism or allotropy. Poly means it is many, morph means changing the structure. Okay, so the definition is like the materials which have same composition but show different crystal structures at different temperatures, that is called polymorphism or allotropy. See, in the figure we have some two axes. Okay, and at y-axis we have the temperature, on axis we have the time. Okay, we have the example, that is iron. Okay, see, in figure you have some things like BCC, FCC, BCC. What is this? BCC means body centered cubic structure, FCC means face centered cubic structure, BCC means body centered cubic structure. You have studied already in the first chapter. Okay, so see, iron from 0 degree Celsius to up to 900 degrees Celsius, it shows the BCC structure. From 900 to 1400 it shows the FCC structure, and from 1400 to 1539 degrees Celsius it shows the BCC structure. Means the material is same, that is iron, but it changing its structure as per the temperature. It is first at the bottom, it is BCC in body centered cubic structure. After heating it above 900 degrees Celsius, it changes from BCC to FCC, and again above 1400 it changes from FCC to BCC. Means the material is same, it just changing its structure as per the temperature. This is called allotropy. Okay, remember the example, that is iron. Next, the second point from this lecture, that is solid solutions. A solid solution is simply a solution in a solid state. It consists of two kinds of atoms combined in a one type of space lattice. Solid solution means here we form a solution with two things, that is solute and solvent. Solute is something, as I said earlier, those having lower composition is solute, though those having higher composition is solute. In the figure you can see with the orange spheres it is a solute, those having blue spheres it is a solvent, and we mix both of these, we get a solution. At a lower side we see the solution, at left side we form the interstitial solid solution, at the right side we form the substitutional solid solution. Okay, so solid solution, it is an alloy in which the atoms of solute are distributed in the solvent and has the same structure as that of solvents. Means solid solution is nothing but a mixture of solute and solvent. Okay, here in the solid state just we replace the things. We cannot mix it properly as in liquid. Okay. Next, we have two types of solid solutions. First is substitutional solid solution. In that we have two things: order or regular solid solution, and second, random or disordered solid solution. And second, we have interstitial solid solution. Okay, we can see it next what it is actually. Okay, so see, this is first substitutional solid solution. See what the definition says: the solute atoms are substituted at the atomic sites of solute atoms. The case is that only size of the solute and solvent must be the same. We will go through the diagram. Okay, see in the figure, the solvent metal atom are in a green color, solute element atoms are in blue color. Okay, at initial all the spheres are in green color. Okay, so it is a solvent. If we placed everything in a blue color, then it is a solute atom. Okay, so at initial we place every sphere here in a green color, so it is solvent. Okay, and after some time we replace some green spheres with a blue spheres. Means what I am doing, I am replacing the solvent with a solute. Replacing means I am forming a solution. Okay, means I am forming a solution of some solvents with some solutes. Okay, so after formation also in the figure you can see there are more number of green colors spheres and less number of blue color spheres, because always in the solution the solvent composition is higher, solute composition is less. Okay, so depending on the replacement, see in figure the blue color spheres are placed anywhere. It is placed randomly. There is no way to place it. Okay, so depending on the placing of a solid atom, we have two types, that is ordered or regular solid solution, or second is random or disordered solid solution. If we place the blue color spheres in a specific order, in a regular order, then it is ordered solution. If you place it randomly anywhere as per your wish, then it is random solid solution. Okay, you are getting or not? Next, this is the one, that is ordered or regular solid solutions. See in the diagram directly, no need to go in the definition. Okay, in diagram we can see the white spheres are of solvents, the orange spheres are of solute atoms. Okay, in this solute atoms are placed in a horizontal line. There is a way, there is a systematicness, there is a regularity. So this solution is called ordered substitutional solid solution. There is a order to place the solute in the solvent. At initial we will have only the white spheres, that is called a solvent, and after some time we replaced the white spheres with the orange sphere, so we form a solution. But when we are forming the solution, we are keeping ordered in that. Okay, we have placed the solute in such a way that it looks systematic. So this solution is called ordered or regular solid solution. Okay, example is Au dash Cu. Au means it is a gold, Cu means copper. This solution will show the same structure up to 400 degrees Celsius. Okay, and main one case is here that the size of solvent and solute must be the same, then and then only we can replace the solute with the solvent. If size is different, we cannot replace. Okay, so this is ordered solid solution. Next, this is random or disordered solid solution. In this, what is the definition? The substitution of solid atoms at the sites of solvent atoms in an indefinite or random order. You can see in the figure also, those are the white spheres are the solvents, and those are in the orange color are the solutes. Okay, so you can see solute atoms or the orange spheres are placed anywhere. There is no systematicness, there is no regularity. where I want, I placed it. Okay, so it is a random placement. Okay, so it is called random solid solutions. There is no any systematicness. Okay, so the example is same again, gold and copper, but at higher temperature, because as you're going to increase the temperature, it will simply change the order of the solutions or the order of the placing. Okay, so this is called random or disordered solute solution. If we place the solute atoms in a order, then it is ordered solute solution. If we place solute atoms in a random way anywhere, then it is called random or disordered solid solutions. Okay, we will go next. This is interstitial solid solution. Okay, directly see in the figure. As we see the green spheres, okay, the green spheres are called solvent metal atom and the blue spheres are called solute element atom. Okay, so see, in first two cases we replace the solvent atoms. In this case we cannot replace anything, just we place something. Okay, because see, in this solution the solute atoms occupy at the interstitial site of the solvent atom. Okay, what is meant by interstitial site? As we see in the figure, we join the four green spheres together. Okay, they have the point contact, so they have a gap in between them. That gap is nothing but an interstitial site, and that interstitial site is placed with or the filled with the solute element atom. So in this case we are placing the solute atom. In first case, two cases, we are replacing the solute atom in a solvent atom. You are getting or not? In first two cases we are replacing the things. In this case we are placing the things. Okay, so in this case it is called as interstitial solute solution because we are placing solute element atom at interstitial sites of a solvent atoms. You are getting or not? You can see in the figure also, because the size of the solute is very small as compared to solvent. In first two cases we have the same size of solute and solvent. In this case the solute atom is very small as compared to solute atom, so that we can place the solute in interstitial site. The best example is steel and cast iron, because in this the green color solvents are nothing but the ions. They have the bigger size, and the smaller atoms or the solute that is in blue colors are the carbon or the boron or the oxygen or the hydrogen and the nitrogen. They are placed at interstitial site because they have the lower size. Okay, so this is interstitial solid solution where we place the solute atoms at an interstitial site of solvent atoms. Okay, you are getting or not? So this is just a difference. In substitutional solid solution, the size of the atom or the size of the solute and solvent is same. In this case, interstitial, we have different size. The size of solute is very small than that of the solvent. Okay, we will go next. This is solid solubility. The last point in the lecture, solid solubility, that is, we can also say it as Hume-Rothrie's rules of solid solubility. Hume-Rothery is a scientist who found these rules. Okay, what is meant by solid solubility? Okay, we can take a general example. If I mix the 1 liter of water with 100 gram of sugar, I stir it well, I form a solution. Okay, I form a homogeneous solution in a liquid form. Okay, next I am going to add another 100 gram of sugar in a liquid or in a water. Again I stir it, again I form the solution. Again I add 200 gram of sugar in a water. Again I stir it, again I form the homogeneous solution. So in this way I add 500 gram of sugar in 1 liter of water. I stir it and I got a homogeneous solution. After that I add another 50 gram of sugar in a same water. I stir it, but I cannot form a solution, or I cannot form a homogeneous solution, because the limit of water to dissolve the sugar is get over. Means the 1 liter of water cannot dissolve more than 500 gram of sugar in it. So that is a limit, or that is the solubility limit of a water to the sugar. Means 1 liter of water have the solubility limit of 500 grams of sugar. Okay, more than 500 grams of sugar we cannot dissolve in 1 liter of water. That is nothing but a solubility limit in a liquid case. Same way, in a solid state we have some factors which defines the solubility limit. Okay, see, in the formation of solid solution, the solubility limit of solute in the solvent is governed by some factors. Which are those? Those are the below we have some 4 factors. Those are like, first one, atomic size factor, second is chemical affinity factor, third is a relative valency factor, and fourth is a crystal structure. Means the solution in a solid state which have solute and solvent, how much extent of solute will be dissolved or will be replaced in the sites of solvent, that can be governed by some factors. Those factors found by the Hume-Rothery, who is a scientist. So it is called as Hume-Rothery's rules of solid solubility. These are the 4 ones: atomic size, chemical affinity, relative valency, and crystal structure. Okay, we will see one by one. First, atomic size factor. What it says? If the atomic size of the solute and solvent differ by less than 15%, then it is favorable to form a solid solution of 2 components. If I take a 2 metals, that is A and B, the difference between their sizes is less than 15%, then they tend to form a solution. And if the atomic size difference exceeds 15%, then they will form a solution, but solubility is limited, that they cannot dissolve more, they dissolve less. So atomic size is less than 15%, atomic size difference is less than 15%, then they tend to form a good solid solution with more solubility. And if the difference is more than 15%, they will dissolve the less, or the solid solubility is limited. Okay, you getting or not? Next, chemical affinity factor. Chemical affinity is nothing but the chemical attraction between the 2 metals. If chemical attraction is more is the solid solubility, and more is to tend to form a solution. See, if chemical attraction is more will be the solid solubility, more will be the formation of solid solutions. Generally, in periodic table, the elements are placed somewhere in the table. Okay, as they are placed widely, if the difference in their placing is more will be the attraction, more will be the affinity, more will be the solubility, and more will be the formation of solutions. If their placing is less, means the difference in their placing is less is their attraction, less is the affinity, less is the solubility, less is the formation of solution. Okay, so in the last statement we can see, generally wider the separation of elements in the periodic table, greater is their chemical affinity. In next slide, relative valency factor. A metal of higher valency can dissolve only a small amount of lower valency metal, and while lower valency metal can dissolve high amount of higher valency metal. In the example you can see, aluminium is equal to 0.04% of Ni, that is nickel, and in lower we have Ni is equal to 5% of aluminium. As we know, aluminium have higher valency, Ni have lower valency. Okay, so in the example you can see, aluminium which is have higher valency, so higher valency metal can dissolve lower amount of lower valency metal, that is 0.04% is a lower amount, Ni is a lower valency metal. So we can simply say that like higher valency metal can dissolve lower amount of lower valency metal, and in below line Ni is having lower valency, 5% amount is more, aluminum have a higher valency. We can say lower valency metal can dissolve higher amount of higher valency metal. Okay, so this is what relative valency factor. In the last one, the crystal structure. The metal having same crystal structure will have the greater solubility, and those have the different crystal structure will have the limited solute solubility. So these are the means the same crystal structure, higher solubility, different crystal structures, low solubility. Okay, so these are the four factors, that is atomic size factor, chemical affinity factor, relative valency factor, and crystal structure. If these four factors will govern the solubility of solute in a solvent. Okay, so this is the first lecture of your second chapter. If you have any doubt, you can contact me. Okay, so thank you for listening well. Thank you one and all.